Good evening, everyone. We are glad to have Aayush Verma with us with the talk titled The Relevance of Mathematics in Theoretical Physics with examples of S-Duality, quantum mechanics, gauge theory, Langlands duality, and all that. Over to you, Aayush.
Thank you. Yes, so I'm going to talk on this relevance of mathematics in theoretical physics. Actually, I wanted to apologize because I have written an abstract semi-technical, but it's not semi-technical as I wanted it to be. But what we can understand from here is motivations from both sides of the world. Okay, so often pure mathematics is criticized as useless now. So what is this definition of pure mathematics? So according to Bertrand Russell, one of the best philosophers and a mathematician, it is pure mathematics is class of all propositions of the form P implies Q, where P and Q are propositions containing one or more variables, the same in two propositions, and neither P nor Q contain any constants except logical constants. And logical constants are all notions definable in terms of the following. Implication, the relation of a term to a class of which it is a member. The notion of such that with the notion of the relation and such further notions as may be involved in the general notion of propositions of the above. In addition to this, mathematics uses a notion which is not a constituent of the propositions which it considers, namely the notion of truth. Well, that was very much notions, but this is what Russell thinks about. Anyways, this talk is not about the philosophy of either mathematics or physics. I just want to clarify what a pure mathematics is. I will mention few parallels from past centuries, especially not last year, actually, last century, between theoretical physics and mathematics. Essentially, how some of the thoughts of both mathematicians and physicists were basically the same. And in recent time, theoretical physics advancements have gone through a serious play of mathematics. There are a lot many examples of such plays, but here we will cover only a few of them, which is basically quantum mechanics, matrix mechanics, S-duality, Young's gauge theory. I have written not theory, but I will not cover it. So quantum mechanics. Now, I assume most of you must have heard what is quantum mechanics. So quantum mechanics is study of microscopic physical systems, such as studying a hydrogen atom. Physically, it represents the one half of knowledge of the physics, with other half being GR, or more generally, study of gravity. Basically, in quantum mechanics, roughly we are concerned about the states, psi, which represents a certain system. So to each system, we have a psi, which basically represents the system. Knowing what exactly psi of a system is not as trivial as in classical mechanics. However, we can know what is the probabilistic distribution of such psi. This psi is governed by partial differential equation, Schrodinger equation, which is some over space R. So you can know the probabilities distribution of some state over some space. Moreover, operators give us relevant values of numbers that we are interested in, such as energy. So for each operator, we have some certain eigenvalues, and those eigenvalues are interesting because those represent some physical quantities. So if you act in a Hamiltonian operator, you have energies with position by the position operator, momentum by the momentum operator, and so on. And these you act on this state side. So the notion of the quantization is based when the commutation relation is established. So this commutation relation must be established. So if you take a course in quantum mechanics, you are taught how to quantize a system. Basically, you are given a classical system, and then you have to quantize it. So in order to quantize it, you must satisfy this commutation relation. X is position and P is momentum. We are also interested in interaction of more than one system, such as entanglement between. So in 1920s, quantum mechanics was studied to explain the atom and related physics, but it was later revised with a more concrete use of mathematics by Heisenberg, known as metric mechanics. In a nutshell, the metric mechanics was use of linear algebra to systemize the quantum mechanics. And this can be thought of. So I assume that most of you are aware with linear algebra. And because in quantum mechanics, it is used very extensively. All because these states which I have here come from a vector space. So this can be thought of understanding these states as vectors and operators as metric functions. So you have these operators which I have here. is Hamiltonian and position operators. So these are basically metrics. So if you know metric operation, this is what it is needed with. Then the eigenvalues for these operators should be physically relevant quantities like energy. And these states belong to a vector space. And when we introduce the condition of a positive definite inner product, then this vector space is called Hilbert space. And the eigenvalue equations are such, like here you have some operators, and here you have some position. Oh, sorry, these are your states, and this is your eigenvalue. These are called eigenvalues. In quantum mechanics, these operators must be self-adjoint. So there is this requirement of self-adjoint because they must be self-adjoint. In quantum mechanics, we are interested in those only because they give the real eigenvalues. And it's a trivial theorem to prove that there are real eigenvalues corresponding to self-adjoint operators. And the eigenvectors form a Hilbert space of square integrable functions as previously. So basically, I'm talking about this vector space. Now, there was a standard attempt to formalize the quantum mechanics with the use of more rigorous mathematics, namely of functional analysis and operator algebra by von Neumann and Francis Murray in their rings of operators series of books. So what we do is we collect the relevant operators actually just like Hamiltonian and position operators and so on, which act on a Hilbert space and form an algebra. Now, I'm pretty sure you must have heard what is an algebra. Simply speaking, on a region, let us say R squared, one can associate bounded and self-adjoint operators, and this will form an algebra. And this is formed famously known as von Neumann algebra, which is a type of C-star algebra. And if actually this will be called von Neumann algebra if this is satisfied, where this is called double commutant of K, and if basically just take a region R squared. So basically, let's say a circle, and in one region, if you define A, the commutant will be A dash, and the commutant of that A dash will be double commutant. So if this is satisfied, we call it a von Neumann algebra. So if you cannot keep up, it's basically what we are doing is we take these operators which act on a Hilbert space, and we call them an algebra if they satisfy this. And basically, they are called von Neumann algebras. And these were studied in these papers, actually 3 of these papers by von Neumann and Francis Murray. So one can interpret these
elements.
Question.
If I could just ask a quick question.
Yeah, sure.
Yeah. So in what case, like, is there an example for why the double commutant of A shouldn't be A? Like maybe some example as to why you can't have a von Neumann algebra in some case?
This is called a double commutant theorem. So if you satisfy this, then only you have a von Neumann algebra. This is a...
Yeah, I mean, if you have like, let's suppose there's a box, and then we have some bounded region, we'll call it A. And so we're saying that this A over here is just the algebra too. Is there any reason why every case isn't a von Neumann algebra? Because it seems intuitive that if you take the commutants...
it's not, because what we... not. Every algebra is not. First, it has to be a C-star type C-star algebra, and then it must satisfy this. In the von Neumann algebra, you have the self-adjoint operators and the bounded ones. So basically, when you have operators, you must smear it, because if you do not smear it, it's not relevant to you. So you have to smear the functions. And the reason why it is bounded is very important as well. So I'm not just calling every algebra von Neumann algebra. They must be bounded and self-adjoint.
Right. And is there a condition on the exterior as well?
Sorry, I didn't get you.
Yeah, is there any condition on the exterior, as in, could it just be a non-compact, slice or something, and then you take the exterior?
Sorry, I didn't get you, actually.
Yeah, I was just basically asking if there's, any condition or any restriction on the exterior. Like I could take a bounded subregion, but I could take the slice to be compact or non-compact. So I was just asking if that's also relevant or not.
Actually, there is this theorem by Borchers, It's on the wedge theorem. You should study that. It's relevant, but not here. It's by Borchers, if I'm right. You can find it. There are these papers by Borchers, review papers by Borchers from 67 or something. There he has mentioned this wedge product. Sorry, these wedges and all.
Okay, thank you.
Yeah. Sorry. So now what we can do is we can call these elements to be physical operations acting on our space. And this space is just a collection of our vectors known as wave functions. So you see, the elements of this are just the operators, and I'm calling them physical operations. So in this case, this space is just the Hilbert space. Anyways, for any simple quantum mechanical system, the description of C-star algebra and Hilbert space are both applicable. This is my first point. The relevance is what it is here, that quantum mechanics was first described in this formalism and later in terms of C-star algebra, and we found that both are equivalent. So most of these stuffs you can do here is basically just represented by a C-star algebra. More formally, one-Riemann algebra if you include the self-adjoint operators. Why it is interesting? In recent time, it has been more interesting. Actually, in this original papers by Von and Murray, they have talked a lot about the projection operators and lot many. It's all relevant in that case as well. Anyways, so in past few years, this has been an active area of mathematics and physics to find the operator algebras of different spacetimes and properties. Slight remark. So basically, I end that discussion here. Slight remark, the classical theory that gives a quantum theory can be vigorized in terms of subjective phase space and a two form, where instead of Dirac brackets and commutation relations, we have Poisson's brackets, and Hilbert space is replaced by phase space. So if you remember, I had a quantization condition here. If you have this commutation relation, you call that a quantum theory. So if you replace that with Poisson brackets, which I haven't shown here, but if you replace that with that, basically you come to the classical theory. So in terms of quantization, when you study quantization in mathematical fashion, what you do is you take these Poisson manifolds and you quantize it. So you change these Poisson brackets to Dirac commutation relations, or that XP commutation relations. There we have this Hamiltonian equation. So basically now I'm talking about classical theory, which is we all have gone through it. So these are your Hamiltonian equations, where H represents a Hamiltonian, and these P's and X are just position and momentum variables. So in this case, where Hamiltonian is just P squared by 2m, and this potential, and we know F is just the minus of dv by dx, then the V, basically you have this. I want you to have two dots here. That is to say double differentiation. And this is what you get here, because V, and we know this. So the symplectic phase space is a way to understand the Hamiltonian formulation of classical mechanics. Of course, there are other rigorization of classical mechanics available, and you can check these Arnold's book for this mathematical motivation. So basically, I just wanted to say not only quantum mechanics, but classical mechanics is also mathematically fashionable in this sense. And this all you study in symplectic phase space and symplectic geometry. So if you have any questions until here. Okay, now we are going to Yang-Mills theory and vector bundles. In this, we are going to see the relevance of differential geometry in Yang-Mills theory. So a gauge theory is a theory which is invariant under certain gauge transformations or locally defined transformations. So basically, it represents degrees of freedom of a theory that are redundant and can be fixed. And it was introduced by Weierstrass. So an example of changing the phase of a wave, for example, if you have a wave and you multiply a phase with it, it is basically a gauge transformation. And this is called a unitary gauge transformation. So now if you see, the psi belonged earlier to a Hilbert space, H, and let's say this phase activated psi belongs to H dash. So this map is just a unitary gauge transformation. And these gauge transformations are basically redundant. They do not change the physical relevance of a theory. Can I annotate? Is that a feature? Oh, no. Anyways, It was realized by Sean O. Young and other people in 70s that Yang-Mills gauge theory and concept of a fiber bundle, a principal G bundle, is essentially this. Now, I'm not sure if all of you are aware with the concept of a fiber bundle or a Yang-Mills gauge theory. So let me recap some. So what is a fiber bundle? So it is defined as a map from some manifold to a base space, where M is a base space and there are some fibers involved in it. So what is this? This is basically a projection from something to something, where E is, let's say, your manifold and M is a base space. And these pi's basically project these on this M. I think there is a very simple example. If you have a hairbrush and there are these fibers, I actually do not know the technical name for this, bristles or whatever you call that. So basically, those bristles are fibers, and they map something to the upward space, and these are called fibers. I think on the Wikipedia this image is available. So this is a fiber bundle. A section of a fiber bundle is a continuous map, which is the in a case this is just the inverse of this pi. So pi takes E to M, and section of this bundle takes M to some subspace of E. So such that for X and E, if you act S on an S on X and then pi on this, then you just get the X band. So a principal G bundle is defined as a fiber bundle from P to X, where P cross G is just the P. This is called a right continuous action. Basically for X in P, and we have XG in P, where G is coming from a structure group. This is called a structure group, where G is a group. A group is just a set with an operation. Now the claim is that a gauge theory and principal G bundle are equivalent. Let us recap some features of gauge theory. So in gauge theory, there is a gauge transformation between variables like, let's call G is a map which maps E to 8 dash. And as I have shared, that these are redundant. Actually, this doesn't change the theory itself. But locally, we define different variables, and all of these are connected by some sort of gauge transformation. So you can imagine this as walking between rooms in your house. That doesn't change the house itself, or you actually. So where A and A dash are gauge fields, and G takes value in the gauge group. And there's a field string defined as this. Now, if you're not sure what you are looking at, this is a differential operator, and these are called wedge products. So a simple example is electromagnetism, which is an U1 gauge theory, where A are vector potentials and F is the field string. So if anybody has taken courses in electromagnetism, they are aware with vector potentials and what is a field strength, at least in electrodynamics. But these are just U1 gauge theory. U1 is unitary gauge theory. So in gauge theories, we usually have a Bianchi identity. In the case of electromagnetism, it is dF equals 0. Now, it is to say that this F is closed. Now, I'm using the terms from something called differential topology and DRAM homology, but it is not relevant. But this F is a true form which is closed here under this differential operator. Now, in a principal G bundle, a connection is defined to be maps which take the value in this structure group G, which is just this. And we have seen both fiber bundles in gauge theory. So fiber bundles, you know, it's some sort of projections from some space to some space. And gauge theory is basically some theory which has gauge degrees of freedom which are redundant. Both has group features, and connections and gauge fields look the same. Both theory has features which are identical. So the next two slides might be technical, but you're welcome to read. So the Yang-Mills theory is described as a G bundle, E goes to M, where M is a Riemannian manifold. And we have the curvature described in this form, as we have said. And the wave equation is given by this, where this is called the Hodge product. And in a Billian case, such as U1, D reduces to D, basically. And you have this, which we have shown here, which is the Bianchi identity. This describes the propagation of the Maxwell's wave. So using this equation 13, you can describe the whole electromagnetism actually. And for the non-abelian case, you have to include this Hodge product. And the waves are non-linear actually. This page is not relevant here, but still. And GR is described by the vector. Okay, they are described in vacuum by this equation, which describes the hyperbolic waves. Means that they are evolution to some Cauchy initial data. And in GR, we have the collapse of the space-time and the light rays cut off. The situation in the quantum gravity is hard because of this. Now, for a gauge group, such as this, we observe classical solutions of Maxwell's equation all the time, which is the light waves. So basically, you have a continuous frequency. You must have seen this spectrum of light. So there is this frequency, this gives this waves, and this frequency gives this wave. And for a non-abelian G, even though there are beautiful nonlinear classical wave equations, we do not observe these nonlinear classical waves in practice. That is because of a phenomenon known as mass gap. And this is still a relevant open problem, and nobody has been able to solve this. So let me reproduce a simple dictionary. Also
just ask a
Young
question. So in the previous slide, you mentioned that there's a collapse of the space-time, and I was just it makes sense when people say that the field strength is it's kind of akin to the curvature tensor, but then again, I don't really see the analogy.
No, I'm not saying. I'm just saying the DF. I'm not saying a GR is described using this. I'm saying DR is described by this equation. It doesn't come from this actually, and that's why I said this whole slide is not relevant to this fiber bundles now.
Yeah, but the field strength tensor is kind of akin to that. So to the Riemann tensor. Yeah. So I was just wondering what the relation was. Okay, sorry.
Okay, let me reproduce a simple dictionary, also called Young dictionary. Okay, so this is basically a dictionary. Here you have gauge field, basically gauge theories, and you have fiber bundles. And you can see the similarities actually. So a gauge is just a principal bundle. A gauge type is just a principal fiber bundle. A gauge potential is just a connection. These are the transition functions. These are the phase vectors. This is the parallel displacement. This curvature is just, actually the curvature is written as just the d times the connection, which is this curvature. And this curvature is just the field strength. The source is not written here. Electromagnetism is a connection on U1 bundle. So mathematically, electromagnetism is nothing but a connection on a U bundle. And these connections are nothing but the vector potentials A. And that's how you describe the whole electromagnetism actually. And these gauge transformations basically take value in some group, and that is called U1. So U1 bundle gives this structure group. Anyways, the isotopic spin gauge field is just a connection on SU2 bundle and so on. These two are very interesting as well. So this is the dictionary which I wanted to imply. And this is very beautiful because here you have differential geometric terms, and which was very famous around 70s. And this is basically some very interesting physics that happened in gauge theory, Young-Mills theories, and so on. So basically, a gauge theory is equivalent to the fiber bundle mechanics. And here is the conversation which Young had with June in 1975. And I'm going to read it to you. When our conversation turned to fiber bundle, I told him that I had finally learned from Jim Simons, another very big mathematician, the beauty of fiber bundle theory and the profound Schoen-Weyl theory. I said I find it amazing that gauge fields are exactly connections on fiber bundles, which the mathematician developed without reference to physical world. I added, this is both filling and puzzling, since you mathematician dreamed up these concepts out of nowhere. He immediately protested, no, these concepts were not dreamed up, they were natural and real. Basically, what they were talking is that it is often believed that mathematicians just dream up things in their dream and they just come and write their papers. And this was not one of them. It's basically two groups were describing same things without interacting with each other. And such was the beautiful duality. Yeah. Anyways, now I'm gonna come to the last part. How much time in this meeting? Okay, let's continue. So S-duality, now we will come to the last part of the talk, which is S-duality. It was a duality found in string theory by Sen, Seiberg, Wetzel, and others. Dualities in string theory play a very crucial role to understand different backwards and how one theory works in a different regime. all 5 kinds of string theories. Basically, we have type 1, type 2A, type 2B, S32, cross 32, E8, E8 are essentially the same in different limits of string theory. A duality is a correspondence shared by two different theories. In mathematics, the Galois theory is a form of duality. We can take an easy example of T-duality found in string theory. So here, let's say you have a cylinder of 1 by r radius, and here you have a cylinder of r radius. According to T-duality, if you have some theory compactified on this, and if you have a theory compactified on this, they are basically the same. Now, if you do not know what is a compactification, basically what you do is you take some additional dimensions. Let's say you have a 10-dimensional theory, but you are only interested in 4-dimensional backwards or 4-dimensional relevant stuff. What you do is you take these 6 dimensions and you compactify over some topology. So here I have taken that to be cylinder. Now what you remain is with 4-dimensional theory and compactified theory. So if I have a compactified theory on 1 over R, and if I have a compactified theory on R, by T-duality, it's basically this. Just like this, we also have an equivalence between coupling constants, alpha and 1 by alpha, which is called the S-duality, where the alphas are coupling constants. So for any gauge theories, let's say any physical theory, you have this alpha. Alpha denotes what is the coupling constant. That means the strength of the coupling. For electrodynamics, it is 1 by 137, which is a magical number though, which is the S-duality. This correspondence between alpha and 1 by alpha is the S-duality. So basically, I want to say that a weak theory and a strong theory are basically same, which is close to the statement of Dirac's quantization condition, which is to see E and 1 by G. This is the electric side and this is the monopole side. Anyway, I'm not going to talk on this. What is found that it has to do with the modular group SL2Z, and the modular forms are just holomorphic functions that transform under this subgroups. Maybe that is technical, but SL2Z is some sort of group, which is where you have the determinant 1. Now, the same group is also found in S-duality in string theory, which can be naively interpreted as electric magnetic. Actually, this has very much wide open mathematical quest. If anybody is taking this, it's very big. And you can be misled by some simple things like SL2Z is directly electric magnetic duality. But for example, if you have a 6-dimensional theory, that's directly evident in that. And this can be found in the groups of Sen, Kapus, and Lichon, Goddard, Newt, Oleg, and Monastery.
Yeah, so I believe we've also talked about this at some point, but I don't remember. So there's also something called the U-duality, which is a combination of the S-duality and the T-duality. Is there any specific characteristic to it, or is it just like a neat thing?
Yeah, it's one of these 3 famous dualities in string theory: S-duality, T-duality, and U-duality. So S-duality naively interprets as a combination of S and T, but it's not widely accepted to be there. In fact, I would be hesitant to call it in that, but it's basically naively interpreted. But in all of these 3, S-duality is the most profound mathematical exploration, so to speak, because SL2Z is directly related to that. I wish okay, just let me see if I have annotation to say.
Yeah, okay.
Yeah. So in SL2Z, you have 2 generators, namely an S and T, and one is basically just taking, let's say lambda to lambda plus 1, and one is taking lambda to 1 by lambda times a factor, which I'm not including right now. And these 2 operators actually are very relevant because T is generated mostly when you have some quantum features. And these S and T generate the SL2Z. And SL2Z is called modular group for many reasons. And SL2Z is very relevant in all of these explorations of, let's say, electric magnetic dualities or even anion duality, which is some sort of SL2Z in such manner. And this was shown by all of these people. Okay? But U-duality, in other hand, is different. And I have not studied it. Actually, I have not found any mathematical implication of it. Maybe there are, of course, there must be. Any other questions? Okay. Yeah. So, a word on Langland's program. Yeah. I should say a misleading word on Langland's program because it's very hard to talk about Langland's program in such short time and in such short exposition. The Langland program is a wide program throughout mathematics that relates the area of representation theory and automorphic forms to the Galoha theory. So representation theory is basically when you take a group and map it to some vector space, basically some sort of this. So, okay. Okay, I'm having trouble with it. Okay, anyways, representation theory is a map from a group to the endomorphism of some vector space. And you study it basically to understand how a group acts on some, it also tells you about the matrices in that representation and so on and so forth. And it's also relevant in physics as well. It's very relevant. And automorphic forms to the Galoha theory. Now, what are automorphic forms? Automorphic forms are generalization of the modular form, and modular forms are just the holomorphic functions. So when you have the SL2Z and these holomorphic functions are called modular forms, and when these are not SL2Z, they become something else. They are called automorphic forms. To Galoha theory, which is the correspondence between group theory and field theory. Now, one of the many Langland's duality is called geometric Langland's duality, which is useful in theoretical physics, especially in string theory and conformal theory. And the statement boils down to the factors of V that a quantum field theory defined using a group G is equivalent to its Langland's dual Gi. Electric magnetic duality is a similar statement, which is given by the GNO paper, which is this paper, Godard, Munoz, and all this paper. They were the first ones to show that this electric magnetic duality can be interpreted using this G and GR, where they have taken the weight and two-weight lattices of these structures. Anyway, so this electric magnetic duality is a similar statement given by GNO paper that G and GR describe the electric and magnetic charges. Now, what is the connection? Okay, if anybody has any rough questions about the Langland's program, please ask.
Yeah. So, what is this Langland's dual group?
Okay, Langland's dual group is some sort of it's not explicit I can make here, but see, for any, let's say G, okay, you can have its character group, yeah? Now, for any G, you have some character group, and that is called dual group. Here, the Langland's dual is basically GGL, where if you have studied Fourier analysis of any group, you know what is this dual group, which is just a character group here. But here, it is Langland's dual in the sense that, see, basically, if you want to understand, there are two sides of Langland's duality. One side is basically telling you these fancy steps of representation theory and automorphic forms. The other side is Galoha theory, and it is represented by a prism. Actually, so you have some sort of prism, and one thing comes in and other things goes out. It goes out is your Langland's dual stuff, and goes in is your G stuff. So these two sides are given by G and GF. So if you want to make very explicit statements about Langland's dual group, it's very hard to do it here. But I can tell you it's very short of, if you know what is Fourier analysis of any group, you can understand what it is. So let's say on A side, you have some magnetic eigenrings, on the B side, you have electric eigenrings. Actually, these are very complicated. But did you get it?
Yeah, vaguely.
Yeah, I wish I had a very simple statement about them, but unfortunately, I do not.
Yeah, I think I'll just
say that these Langland groups describe the magnetic charges. Okay, these Langland groups describe the magnetic charges. The co-weight lattice of this, the magnetic charges takes place in the co-weight lattice of this magnet, which is the dual. Got it?
Yeah.
So what is the connection? We can argue that the electric magnetic duality is just another lighter reformulation of geometric Lagrange duality, which was basically this paper by Kapustin and Nixon. In fact, geometric Lagrange duality provides a rigorous definition of mirror symmetry. Mirror symmetry, okay, once again, it's very hard to explain. It's also one sort of symmetry in between compactified space-time. So in string theory, you study this mirror symmetry where you have some A sides and B sides of some theory, and they are basically the same thing, which in turn defines the dualities in a way that can be understood. This also provides a way for theoretical physics to learn from algebraic geometry, representation theory, number theory, and category theory, and to cultivate a common ground between mathematicians. Actually, I must explain here that geometric Lagrange duality is one of those Lagrange dualities. You also have a local, you also have a global, you have so many Lagrange dualities. It's impossible to study all of them. There's an analytic Lagrange duality. Geometric Lagrange duality is very close to part of the physics, but not all of them will be very close to physics actually. So, a bridge between, sorry, I cannot read, mathematics and physics. What we have discussed so far in this talk is how some of the physics are basically mathematics and vice versa. This depicts that most of us who work in accurately don't actually do the right work, and somehow physicists do the work of mathematicians and sometimes their role work. Right now, the hottest part of the mathematical physics is supergravity and alignment programs. In this, my view, of course. But one thing that can be realized that discussions between mathematicians and physicists must be held in order to learn what is happening in the other part of the space. As it is evident that sometimes it is just one word written into it. And here is my favorite physicist and his coach. And he speaks, the most powerful method of advance is to perfect and generalize the mathematical formalism that forms the existing basis of theoretical. Okay, I'll end now. Thank you for listening. Any questions? You're welcome.
Yep. So I think on that last note, actually, it's true because the way in fact history has worked out is that mathematicians have done something like algebras or whatever. In some cases, both of them have happened at the same time. But for instance, differential geometry was always there before Einstein came along. So there's also a question of, do physicists need to adopt the language of mathematics more before cultivating physicality into their models?
But actually, here would not have been developed by a mathematician. It needed some intuition. So what I mean here is, I know that's what I'm saying. Physicists work in isolated zones and mathematics work in their eyes. And basically, all of the times they are doing the same thing. Sometimes it represents some physical nature, as physicists are concerned. Sometimes it represents some abstract nature, which mathematicians are. Both of them are doing their own work, but sometimes this is basically the same thing happening in two different ways. And if you are able to contact each other, that's very helpful because, as I have told, what Chern and Young discussed, it's very profound because at that time, these discussions were happening alongside gauge theory and fiber bundles, all of these happening at the same time. Actually, they were understanding it in a very same time. You can read this paper by O and Young in from 75 or something. They have described this dictionary in a very good fashion. Now, if Einstein would not have developed GR, of course, somebody could have. It's not like nobody would have not done that. But see, we cannot talk about the alternate history, can we? Anyways, I just want to say physicists have some intuition and they are necessary because mathematicians alone are not capable of defining the whole knowledge concept. Mathematicians have their rigor, their brain. Physicists have their personality and their vision. And now, if you compare all of these, of course, this comparison is wrong. But once you understand the relevance in one field and the other field, it becomes very, very rich for you. And I have just talked about math and physics, but physics and math is very relevant as well. For example, you have this string theory conjectures, which is solved by mathematician concept. Now, there are many mathematicians who are working on string theory itself. Jim Simons worked on it. Michael Atiha worked on finance, and there are many. So yes, that's it.
Yeah, I think the other feature is also that mathematicians like to generalize things to n dimensions. And the only difference between mathematicians and physicists at a certain point is, well, the physicality is just that we end up doing n equals 4 and not n equals n. So I
D
think,
equals N.
yeah, I mean, d and something. But yeah, I mean, that's actually the case because also d equals 4 happens to be very interesting, math perspective because of infinitely many structures. And d equals 4 is also very strange in the gravitational setting. So yeah, that's, I think at a certain point they
We
have to
talked
go
about
hand.
concave conjecture. Concave conjecture was not only solved in 3 dimensions. Sometimes it is 1 dimension, sometimes it is other. I just wanted to say, okay, yes, physicists. Also, this is also sociological implication that physicists are advised to work on problems which solve the real world, and in one sense or the other, they are doing that. And mathematicians are interested in some objects and their morphisms. This is what they are doing. So their generalization is biased. Ours is sociologically biased. So that is what I can say.
Yeah.
But physicists should take much more lessons from mathematicians, and mathematicians should take lessons from physicists. So what I wanted to say is interplay between them is very necessary for the advancement, because such a time like ours, where physics doesn't have physical relevance, such as such like at last century there were these particles being discovered and so on. Now we do not have that. Why? Because I don't know, we have exploited all of our energy sources. We cannot go beyond some energy. There are some problems with our calculations. Anyway, the knowledge must progress on, and this was the part of the talk.